Hello and welcome to a revision session from the Further Maths Support Programme. Today we're going to be looking at Edexcel Mechanics 3, and this is the first part of that module. We're going to be looking at variable acceleration, variable force, and some simple examples of simple harmonic motion questions. Topics we're going to be looking at today are, as I say, variable acceleration and force, and we're going to do some basic simple harmonic motion. If you're interested in revision for any of these other topics, you'll find that those are available in separate recordings. Okay, so taking a look at the specification for the variable acceleration and basic simple harmonic, we start with kinematics, and when we're dealing with kinematics, we're going to be looking at acceleration as a function of displacement or time. And we have various expressions for acceleration that we're going to be using here. Specifically, we're going to look at dv dt, where acceleration is a function of time. We're also going to consider v dv dx, which is the result of a chain rule differentiation, and that's used where acceleration is a function of velocity or displacement. Just to verify that chain rule differentiation there, dv dt, the rate of change of velocity with respect to time, is acceleration, but using the chain rule we can write that as dv by dx times dx dt, and that's also dx dt there is the equivalent of v here. Okay, so we then extend the acceleration work, the kinematics work, into dynamics. This is where we start to look at forces as well. And we're going to need Newton's laws of motion. Specifically, we're going to be working with Newton's second law a great deal in this session, and we're going to be looking at using Newton's second law where the force that we're considering is variable. We're then going to take a look at simple harmonic motion, which is a specific case of dynamics, but today we're just going to look at the section of simple harmonic motion that uses the very basic kinematics ideas, so looking at the acceleration. The later part of simple harmonic motion, where you start to look at the dynamics of that, i.e. including forces in the systems, will be covered in a later session. Okay, some ideas then of variable acceleration and force. Just to revise here, that this ladder shows how displacement, velocity and acceleration are related to each other. If you differentiate as you go down the ladder, so D for down the ladder is differentiating, displacement differentiates with respect to time to give velocity, and velocity differentiates to give acceleration, etc. In the opposite direction, we're integrating, so if you have an expression for the acceleration, you can integrate it to give an expression for the velocity, and integrate again to give an expression for the displacement. Alternatively, in the M3 course, we can also jump that middle stage. If we have an expression for the acceleration in terms of displacement, we can actually integrate using the alternative form for the acceleration and go straight to an expression that connects velocity and displacement. Here in these clouds we have various expressions, various terminology for, in the first one, displacement. In the second cloud we're looking at velocity, and in the third cloud we're considering acceleration. And I just wanted to make sure that all of these types of terminology were familiar to you. We're very used to using x for displacement, also y is often used for displacement, and if you're dealing with vectors, r is often used for a displacement as well. I've included a in this first cloud here because a is often in mechanics used for a distance, as well as for an acceleration. We tend to reserve a for acceleration for where a is constant. The second cloud here shows our different versions of velocity. X dot and dx dt are exactly the same thing, just slightly different notation for those. And over here in the acceleration column we've got v dot and dv dt, those two are the same thing. X double dot and d2x by dt squared are the same thing. A, as I say, is usually reserved for constant acceleration, and this is our crucial new part of acceleration for M3, this idea of v dv dx, where you're relating the acceleration to the velocity and displacement instead of time. Okay, so let's think about some generalizations regarding variable acceleration and force. Newton's second law is the absolute king of formulae in this topic, so Newton's second law used more than anything else. I try to remember this as resultant force is mass times acceleration, and all dynamics questions pretty much will use resultant force is mass times acceleration in some way. Newton's second law then can be simplified to give an equation of motion. That's usually a differential equation for the acceleration in terms of x or t, which is then solved using integration of some kind. One specific case of variable acceleration and force that you need to be aware of is the concept of gravitation. So I have here a planet. It's usually the Earth, but not always. So we have a planet here and a particle which is shown at a distance away from the centre of that planet. And in gravitation, we're looking at how the force acting on that object behaves as the object moves closer or further away from the planet. We need to know that in gravitation, force is proportional to the is inversely proportional to the square of the distance between the centres of mass of the two objects. So I've shown here the distance from the centre of the planet being given as x. So the force pulling this object back down towards the Earth is given by some proportion of 1 over x squared. We do need to be careful with direction when we're working on gravitation questions, and I'll show you that in just a moment when we look at an example. We generally need to consider the base case at the surface of the Earth. We know at the surface of the Earth that acceleration due to gravity is given by g, approximately 9.8 meters per second squared, and that's often used to work out the constant of proportionality in a gravitation formula. Do check where x is measured from. This is an important point. In the diagram that I've shown here, I've shown x as being the distance between the centres of mass of the planet and the particle. Occasionally you'll be given a question where x is measured from the surface of the planet, so you do just need to be a little bit cautious to make sure you've read the question carefully and you're using the right displacement measure. We're going to use Newton's second law, and again, just to mention so nobody misses it, it's absolutely crucial that we take care with direction in these questions. So let's take a look at an example, and if you want to pause the recording here and work through this question, this is a good moment to do that. I will give you a moment to do so if you choose, and then I'll be working through the question on the screen here when you're ready. Okay, so let's work through here. You're given that the particle's moving on the positive x-axis. I'm just going to draw a little sketch for myself. I always find it useful to draw a sketch diagram in all of these examples. So here is my particle moving on the x-axis, and it's moving only on the positive x-axis. That's going to be important in a minute. The acceleration of p is 7 minus 2x, and notice here that that is measured in the positive x direction. That's crucial information. We do just need to double check that we've got the direction of our acceleration correct. So 7 minus 2x is our acceleration here. X is increasing in this direction, and we can form our differential equation using Newton's second law. Oh, sorry, we don't need Newton's second law here because we've got no force, but we can form our differential equation. We know an expression for the acceleration. We notice that we're looking to find the distance of p from O when p first comes to instantaneous rest. So what we're comparing here is x and v. We're thinking about velocity here. So we choose our acceleration formula in order to make best use of that. I would suggest we need to use v dv dx for our acceleration formula because it connects together the variables that we're wanting to use. So v dv dx is 7 minus 2x in this case, and that's a separable differential equation, so we're going to split it so that everything to do with v is on the left hand side and everything to do with x is on the right hand side. Like this, putting our brackets round so that everything is integrated with respect to x on the right hand side. I'm also going to add some limits onto this integration. If you want to, you can work with a constant of integration in this case. I'm going to just show you the example using limits. So let's look at our limits here. When t is 0, p is at O. That means that x is 0 and it's moving in the positive x direction with speed 6 meters per second. So I know that when x is 0, i.e. it's at the origin, v is positive 6. So I can put those matching limits in. I'm interested to know the displacement here when v is 0, so I'm just going to make my limits up there 0 and a matching x. Okay, so I'm then going to carry out my integrations. On the left hand side I'm going to end up with v squared over 2, and that's between 6 and 0. That does kind of feel slightly back to front, but it will still work out. And on the right hand side, 7x minus x squared, and that's between 0 and x. Let's put those limits in. I've got 0 squared over 2 is just 0, minus 36 squared, sorry, 6 squared over 2, that gives me minus 18. And on the right hand side, 7x minus x squared, and when I put the 0 limit in, nothing changes. So I end up with a little quadratic here. That's going to give me x squared minus 7x minus 18 equals 0. And that's nicely factorizable. Factorizable, is that a word? X minus 9 times x plus 2 equals 0. We know therefore that x equals 9, or x equals minus 2, negative 2. But we can eliminate this one, because we know that it's moving on the positive x-axis. It told us that in the first line here. So we know that x is greater than 0, so our answer then is that x equals 9 when v is 0. And that's our question done. Here's a second variable acceleration and force question. Again, we're dealing just with the acceleration of p here, and this time you can see that p is, that the acceleration is in terms of t. I almost forgot there to just give a pause. If you'd like to stop the recording at this point and work through the question yourself, now's the time to do it. Okay, so I'm going to get going with the solution here. So this time we have our particle moving on the positive x-axis again. So here's our particle, p, and we have an acceleration of magnitude 3 over t plus 1 all squared. But notice this crucially important wording here. That acceleration this time is directed back towards O. We do need to be absolutely particular with these directions in this question. So x increases in that direction, and I'm going to also put in a velocity v in this direction, but the acceleration is negative in this case. Okay, so because we're using an acceleration that's in terms of t, we're going to use dv dt for our acceleration expression. So 3 over t plus 1 squared, make it negative, that's going to be equal to dv by dt. And in order to solve that differential equation, I'm going to integrate both sides with respect to t, or separate the variables and integrate. That gives me negative 3 times t plus 1 to the negative 2 dt is equal to the integral of dv. Again, I can put some limits onto here. I know that when t is 0, the particle is at the origin. Well, that's no use to me here, but it's moving with speed 2 along the x-axis in the positive x direction. So I know that when t equals 0, v is positive 2. And I'm interested in finding a general velocity at a general time, so those are my top limits there. Perform the integration on each side, and on the left hand side I'm going to get 3 t plus 1 to the minus 1 between 0 and t, and on the right hand side v between 2 and v. Substituting in my limits there, I get 3 t plus 1 to the minus 1 minus, now just be cautious here, we're putting a 0 limit into this expression, but we don't get a 0 result out. When t is 0, this bracket is 1, so this expression becomes 3 over 1, which is just 3, and over here v minus 2. So if we simplify that a little bit, I'm just going to add 2 to both sides and make the fraction back into a fraction. That's going to give me v is 3 over t plus 1 minus 3, and that's the expression that they were asking for in the question. Okay, so crucially, make sure that negative is included in there, and you should be able to get that to work through nicely. Okay, second part of this question then says find 3 significant figures, the distance of p from O when p is instantaneously at rest. So we want v to be equal to 0. Well, this is our expression for v that we've got here. This is what we proved in the first part of the question. So v equals 0, we want 3 over t plus 1 minus 1 to be 0. That's going to give me 3 equals t plus 1. So I'm looking to find the displacement of P from O when t equals 2. Alright, so that's going to be useful in a moment. At the moment we don't really have any information about the displacement. We know the velocity in terms of time, and so we can use, again, a differential equation to get an expression for x by replacing v with dx by dt. Rate of change of displacement with respect to time is velocity. So the expression that we have for our velocity, make that equal to dx by dt. And then again, separate and integrate. So on the left-hand side we've got dx, and on the right-hand side we're integrating 3 over t plus 1 minus 1. And we're doing that with respect to t. Again, we can put some limits onto this one. We know that when t is 0, displacement is 0 because it starts from the origin, and we're looking to find the displacement x when t is 2. We work that out up here. So left-hand side becomes x between 0 and x. Right-hand side we're going to need a logarithm for this one. We get 3 log t plus 1, and then 1 integrates to t. Again, you can do this with a constant of integration if you want to. It will work out exactly the same. We put our limits in. The left-hand side is just x. The right-hand side becomes 3 log 3. That's putting the 2 in place of t, minus 2. When we put 0 in here, we get 3 log 1, which we know is 0, plus 0, which obviously isn't going to make any difference. So we can pop all of that into our calculator because it asks you for an answer to 3 significant figures. If we pop all that in our calculator gives us 1.30. Do just watch the rounding on that one. I think it comes out 1.295 something. So 1.30 to 3 significant figures is our final answer there. Okay, so here we're looking at a gravitation question. If you would like to pause the recording at this moment and have a little go at the question yourself, then please go ahead. Okay, so I'm going to move ahead with the solution now. So a little sketch. First of all, here's my planet, here's my particle, sorry, planet Earth in this case, isn't it? Here's my particle. Please excuse my not very good straight lines here. The particle has a force which I'm going to call F, pulling it down towards the planet, and the distance between the centres of mass of the two objects, the Earth and the particle, is given by x. The radius of the Earth is given by r. That's going to be used in just a moment. I'm also going to draw in the particle at the surface of the Earth. Because it's got mass m, its weight at the surface of the Earth, i.e. the gravitational force on it, is given by mg. And we're going to use that, as I mentioned earlier, as our base case in here. Now, it tells you that the magnitude of the force is inversely proportional to x squared, so we can say from that that F is some constant k over x squared. That's the information that we can get from that inversely proportional to x squared statement. So that's a good start. We can then use our base case, but tell the examiner that's what you're doing. So at the surface of the Earth, you know that x equals r, the radius of the Earth. You also know that at the surface of the Earth F equals mg, because that's the weight of the particle on the surface of the Earth. Only on the surface of the Earth. That gravitational acceleration will change as it moves away from the surface of the Earth. So, but we do know that base case, that when x equals r, our force, our gravitational force equals mg. So that tells us then that mg equals k over r squared. That's just substituting this information here into our original formula, and we can rearrange that to give us k equals mg r squared. And if k equals mg r squared, then F, the force that we're looking for, is going to be mg r squared over x squared, which is what they asked us to show. Okay, it feels like a sort of a very basic question, but it's crucial that you give the examiner enough information to justify that you understand just what you're doing. Okay, so again, if you want to pause and work on the second part of this question for a moment, now's the time to do that. And I will start on the calculation again. Let me just repeat that diagram here. So we have our particle in two different places here. First of all, it starts from the surface of the Earth. Whoops, oh dear, sorry about that. Starts from the surface of the Earth, where its distance from the centre is r, and it moves so that it's a further distance r above the surface of the Earth. Down here, it's got speed 3u, and up here, it has speed capital U. Okay, and we're going to use Newton's second law here, because we're dealing with forces and acceleration. We're trying to find out something connecting speed, etc. So using Newton's second law, the force on our object is given by our force that we came up with in the first part of the question. So we know that that's mg r squared over x squared, just generalising. Now here's the very most important part. Notice that the object is moving upwards, away from the centre of the Earth, so x is increasing, but the force acts downwards, so we must make absolutely sure we remember to put that negative in there. That's crucial that we get our directions correct here. So that's our force. We said resultant force is equal to mass times acceleration, so I'm going to make that equal to m times the acceleration here, and I'm going to choose to use v dv dx but for acceleration because I'm interested in connecting together velocity and displacement. There's no time issue in any of this question. Okay, so we have our differential equation here. We can simplify this to give us our equation of motion just by cancelling out the masses, and we're then going to separate and integrate in order to be able to solve this equation. Everything to do with x can come onto the left hand side, so I'm going to write that as minus gr squared over x squared dx, and on the right hand side I'm integrating v with respect to v. Again, I'm going to put limits on here. If you choose to, you can do this using constant integration. It's fired from the surface of the Earth, so that's where x equals r with speed 3u, so I'm going to match those limits under here. Then when it reaches a distance of 2r above the centre of the Earth, so r above Earth's surface is 2r above Earth's centre. When it reaches that point, it's got velocity u, so we match those limits across here. As I say, nothing wrong with doing this by constant integration if you prefer. The left hand side there is going to integrate with, this is minus x to the minus 2, and if we raise the power by 1 divided by the new power, we're going to end up with gr squared over x on the left hand side here between r and 2r, and on the right hand side with v squared over 2 between 3u and u. Substituting in our limits here gives us gr squared over 2r minus gr squared over r is equal to u squared over 2 minus 9u squared over 2. And just doing a little bit of tinkering and rearranging on the fractions in there should give us 8u squared equals gr. So u, which is what we're looking for, is going to be the square root of gr over 8. Okay, let's move ahead from there. That's a fairly typical gravitation question, by the way. Okay, so now we're going to take a look at some simple harmonic. We're just going to start with very basic simple harmonic here. So these are simple harmonic questions that don't involve a force at the moment. As I say, that's covered in a later recording. A reminder of notation: you need to be aware of these variables as being standard requirements for simple harmonic questions, and you must learn these formulae off by heart. Particularly, you need to be very well aware of this formula here. If a particle's equation of motion is not in that form, then that particle is not performing simple harmonic motion. This says that the acceleration is proportional to the displacement and directed back towards where displacement is 0. If a particle has that equation of motion, then it's doing simple harmonic motion. If it's not, then it's not doing simple harmonic motion. And as I say, these formulae will need to be learnt off by heart. Particularly, it's worth mentioning this formula here. This one is valid if when t equals 0, x equals 0, i.e. if we start the clock when the particle is at the centre of the oscillation. and this one is used if when t equals 0, x equals a, the amplitude, i.e. you start the clock at the furthest part of the oscillation. This one is used for a start point, which is more generalized. Can I just make a particular plea here? You must be working in radians if you're dealing with simple harmonic motion. The trigonometry in here will fall apart if you try to work in degrees, so it's absolutely crucial that you make sure, if you're using simple harmonic motion in the exam, that your calculator is in radians mode for any time that you use it. Okay, so a question on basic simple harmonic motion. Again, if you'd like to pause here and work through the question, this is a good moment to do it. And I'm going to work on that solution here. So the first thing we have to do is prove that P is moving with simple harmonic motion. Now, we said on the previous slide that in order to prove that something's moving with simple harmonic motion, we have to show that the acceleration is proportional to the displacement and directed back towards where the displacement is 0. So we have to show in some way that the acceleration is minus omega squared x. So at the moment we have an expression for displacement in terms of time. If we differentiate that with respect to time, we're going to get an expression for the velocity. So differentiating sine a third pi t, we're going to put the third pi outside, and sine differentiates down to cosine. So we end up with 5 times pi by 3 cosine pi t over 3. If we differentiate that a second time, again we need to, using the chain rule, we need to multiply by a factor of pi over 3. So I'm going to make that pi squared over 9 there. The cosine differentiates to a negative sine, so we've got a negative in front there. Sine of pi t over 3 in here. And I'm just going to slightly rewrite that to show that that's actually minus pi squared over 9 times 5 sine pi t over 3. Sorry, that's not what I meant to write. Pi t over 3, which means that x double dot is minus omega squared, sorry, minus pi squared over 9 times x. So this now matches our expression here. So we need to make a little statement. We need to say something along the lines of acceleration is proportional to displacement and directed towards the point where displacement is 0 Okay, so we've got this negative proportional. Okay, this is simple harmonic motion. Okay, we're then asked to find the period in the amplitude of the motion. Well, we can see the time period for this oscillation in the expression for the displacement here. This is a transformed sine curve. You can also see it in the simple harmonic formula down here. If this is minus omega squared x, then omega is going to be pi by 3, which means that the period of this oscillation is going to be 2 pi over pi by 3. That's 2 pi over omega from the formulae that you need to learn off by heart, and that simplifies to 6 seconds. The amplitude is even easier to find. So the amplitude of this motion is 5 here. You can see that directly from the displacement expression. So amplitude is 5 meters in this case. Maximum speed, one of the formulae that you had on the previous page, Vmax equals omega A. Maximum speed is given by omega times amplitude. So we've got our pi by 3 omega and our 5 amplitude. So 5 pi by 3 gives us the maximum speed of that particle as it passes through the mean point. Just finishing off the last little part of that question, so we've got our x double dot is minus pi squared over 9x, time period or let's just write omega down as well. So omega was pi by 3, amplitude was 5, and then down at the bottom here, this last part of the question tells you points A and B are on the positive x-axis such that OA equals 2 meters and OB equals 3 meters. That's not necessarily at the amplitude of the motion, I've just shown it there. 2 meters and 3 meters. Time taken to move directly from A to B. We can use this original equation again to show that. So if we say that it's at A at time t1 and at B at time t2, then we know that 3 equals 5 sine pi t2 over 3. And again, checking our calculator is in radians mode, we can solve that. T2, and calculator gives about 0.614, etc. Keep that nice and accurate in your calculator, and do the same for point A. So at A, 2 equals 5 sine pi t1 over 3. And again, using your calculator to solve that gives t1 0.3929-ish. And then the time that you're looking for is the difference between those two. And again, watch the rounding on your calculator. If you're going to go to 3 significant figures, I think that comes out 0.222 seconds. And that's to 3SF. Okay. So that brings us to the end of this session. As I say, if you're looking at revision for the other topics in Edexcel 3, there are further recordings available. I hope you found that useful. This slide tells you a little bit more about what the Further Maths Support Programme does, and if you're interested to find out more information, I strongly recommend a visit to our site at www.furthermaths.org.uk. Thank you for listening.